Hey everyone, Mr. Newman here, and today we're going to learn about evaluating limits. So first of all, you remember from before that we found the limit with a graph, such as this, where we look at, okay, what if x is approaching 1 from the left, and then from the right, those are going towards the same point. The point is 1, 2, so the limit as x approaches 1 of f of x is 2. We also evaluated or found the limit using a table. And in this situation, what we did was we looked at, okay, well 0.9, then 0.99, then 0.99, that's getting closer and closer to 1. So as x approaches 1, 1.8, 1.98, 1.998, those are getting closer and closer to 2. So the limit is, as x approaches 1, is 2. And the same thing happens when we're getting closer to 1. And those numbers decreasing it closer to 2. It's important that we test both sides of the limit, both from below and above, as you guys might remember, and I'll explain that more later in this video. So, how do we find it algebraically? That's the topic of this video. Well, here is our function, and so we want to find the limit as x approaches 1. You notice when we plug in 1 into our function, we get dividing by 0, so that's a problem. So we can't just plug in the number. But what I'm going to do is I'm going to write out the function like this. The limit as x approaches 1 of 2x times x minus 1 over x minus 1. This technique is called the dividing out technique. And what I'm going to do is I'm going to rewrite that just so I've got it written out there and I can mess with it. Notice x minus 1 is on top and on the bottom. And so when we're within a limit, we can actually divide those out. Now, a quick word of caution. I wanted to point something out to you guys. Are these two functions equal? Is 2x times x minus 1 divided by x minus 1, is that equal to 2x? It actually is not. And the reason it's not is because of this hole right here. They're actually essentially the same everywhere except for the one on the left. The function on the left has a hole at x equals 1, and the function on the right does not have a hole at x equals 1. So they are not actually equal functions. However, because they're similar everywhere except for that hole, when we're dealing with limits, we can actually divide those out, because the limit doesn't care what is actually at the value. The limit only cares what's around the value. And so we say when we get really, really, really close to 1, then that's another way of saying the limit as x approaches 1, what would that value be? Whether or not there's a hole there. So that's why we're allowed to divide those out, and we get that the limit as x approaches 1 of the whole thing is equal to the limit as x approaches 1 of 2x. Without limits, we would not be allowed to divide those out and continue on as if those were the same function. Now that we've divided that out, notice that 2x is a nice, pretty, continuous function. What does that mean? That means it has no jumps, no holes, and no gaps. We're not dealing with the same function anymore. We're dealing with 2x. The only reason we can do this is because we're talking about the limit, and the limit of these two functions is actually equal. So now that we've divided that out, and the 2x is continuous, we can simply plug in 1. Now the quick rule, and I want to put a little caveat here because there are definitely cautions to this rule. But the quick summary of this rule is that if you can plug in the number into a function, then you may do that at that point to find the limit. There are a few exceptions. One of the exceptions is piecewise functions. Another exception is if you're at the edge of the domain. So for example, the square root function has the domain x is greater than or equal to 0. If you're at the edge of that domain, you're not allowed to plug in, or it's not okay to plug in the value to find the limit, and we'll talk about that why later as well. But right here, 2x, that's a nice continuous function, goes left and right forever. So I'm just going to plug in 1 in for x, because we're looking at when does x approach 1? Well, because it's continuous, it's equal to it at the value x equals 1. So we plug in 1 and we get x that's equal to 2. Notice that's the same as our value that we got from the graph, and that's the same as the value we got from the table. So by dividing out, as long as we're within the limit, we can do that and find the value algebraically. Let's try that out with another one. Right here, the limit as x approaches -3 of x squared plus x minus 6, all divided by x plus 3. Well, you notice here, it doesn't look obvious about what we can divide out, so the first thing we're going to have to do is we're going to have to factor the numerator. Once we factor it, then we notice, oh, now there's an x plus 3 on the top and the bottom. So we can divide this out only because we're within the limit, and we get the limit as x approaches -3 of x minus 2. Those two functions' limits are the same, which is why we're allowed to divide that out. And now, because it's a nice continuous function, we can plug in -3, and we get -3 minus 2, which is -5. I want you guys to notice one more thing before we go on to the other one. Two things. First of all, how would you check your work? You can't obviously go back to the original function and plug in -3 because -3 is a problem number. You plug in -3, you get 0 in the denominator. So what I would recommend for checking your work on these is I would recommend either using a graph or a table, and you can use your TI calculator to do that. What you want to do is you want to test values very, very close to the function, and especially if on the graph you can see it and approximate it, you could see, oh, does that look like it's about -5? Usually if you mess up on the algebra, you don't get something close like -4, you get something way off, like 25 or -15, okay? So, check with the graph or table. Last thing I want you to notice is see how I write the limit as x approaches -3 in front of every algebraic expression until we evaluate it. Until you've plugged in the value for x or the value for your variable, you need to keep writing the limit because they're not equal if we're talking about outside of a limit. So always remember to write the limit, even though it seems like you're doing a lot of writing and it's kind of burdensome. Always write the limit as x approaches whatever before each function until you've plugged it in, so to speak, until you've evaluated it. All right, go ahead and try the next one on your own. Now that you've tried it, I'll show you how to do it. You got limit as x approaches 2, and we factor the top because it was a difference of squares. Then we divide those out, and we get x approaches 2, limit as x approaches 2 of x plus 2. We can plug it in because it's a nice continuous function. And we get 4. For the next one, go ahead and try that one out before I do it. Okay, now that you've tried it out, the trick here is that denominator can be factored by grouping. And you could rewrite it like this, but I'm going to put a 1 right in front of there just to see the grouping a little more easily. When we factor that fully, we get x squared plus 1 times x minus 1 in the denominator. Those x minus 1s can be divided out. And now, even though we still have a variable in the denominator, the number 1 is not a problem number anymore, so we can plug it in. We plug it in and we get 1/2. So, the rationalization technique. Sometimes, in this situation, we actually rationalize the numerator. Now, rationalize means to turn it into a rational number. With that square root there, that can give rise to irrational numbers. So by rationalizing, it's another way of saying get rid of the square root or get rid of the radical. You guys are familiar with getting rid of the radical in the denominator because a fraction is not simplified if you have a square root in the denominator. However, in this situation, oftentimes we actually need to rationalize the numerator instead of the denominator in order to get a function where we can plug in the problem value. So let's see what that looks like. Well, if you remember, I'm going to write out as x approaches 0 of our function. We can't plug in 0 for x because of the denominator. But in order to rationalize, what you do is you multiply by the conjugate. What's the conjugate? Well, one other thing, you guys, you notice the little lip I put there on the square root because the minus 1 is on the outside of the square root. That little lip helps it make it more obvious to me. What you do is you multiply by the conjugate. So in this case, the square root of x plus 1 is the conjugate of the square root of x plus 1 minus 1. Notice how those two changed. So you change the Find the opposite of the second value. Let's multiply the numerators there. So I'm going to use a Punnett square. We have square root of x plus 1, and then minus 1, and square root of x plus 1, and then plus 1. When we multiply that out, we get x plus 1. That's negative root x plus 1, positive root x plus 1, and negative 1. Well, notice a lot of things happen here. First of all, those two are equal and opposite, so they add up to 0. And we also get plus 1 and minus 1, so all of that just becomes x, which is pretty nice. So I'm going to rewrite this. The denominator I'm going to leave factored out. You're going to see why in just a second. And the numerator I'm going to put the x there. So let's divide out the x's, because that was our problem value. And now you notice our fraction, we can plug in the number 0, and it will not cause an issue. It's also not near a boundary, which is important because the boundary would be negative 1. If we plugged in negative 1, that would be because we can't plug in anything smaller than negative 1 because of the square root, negative 1 would be an issue. But 0 is perfectly fine, and you can graph it to check to make sure that it's continuous at that point and it's not the edge of a boundary. So we're going to plug in 0, and we get 1/2. All that to figure out 1/2. Great. So let's talk about a few more things. First of all, one-sided limits. If you can see, I tried to make the font really large. Do you guys see how there's a negative there? That actually doesn't mean negative. That is a way of saying what is the limit as x approaches 2 from the left. So let me show you what that looks like on this graph. That's saying as we're getting closer and closer to the right, what does that look like from the left? Or as we're going to the right from the left, okay? And this value here is going to be negative 1 because that's the output of that value we're getting closer and closer to. Look on the right side. Oh, with something important. It is not negative 2, okay? It's actually getting closer and closer to positive 2. But that minus is just from the left. Real quick, that minus is kind of like it's, I think in the formatting it's like an exponent, so it's just up high and kind of smaller. That's the way they write it, okay? On the other one, you notice the positive. That means from the right. So what is our function as we're coming in from the right there, like that, okay? As we're coming in from the right. Well, as we're coming from the right, we get closer and closer to positive 1. So in this situation, the limit as x approaches 2 from the left of that function is negative 1, and the limit as x approaches 2 from the right is positive 1. This reminds me of an important theorem. The limit exists if and only if the left limit is equal to the right limit. Now in calculus you'll see this in a lot more formal language, but in other words, those two values, they have to approach the same number in order for the limit to exist. So we're kind of talking about 3 limits. There's a left limit, a right limit, and an overall limit. The overall limit only exists if the left limit and the right limit are the same. Okay? If they are not the same, otherwise the limit does not exist. And instead of calling it overall limit, we just call it the limit. Okay? So if I don't specify right or left, I'm just talking about the overall limit. We also abbreviate does not exist with D and E. So does not exist. How do we apply that in this situation? Well, look at this periodic function. We have 4 minus x when x is less than 1, and 4x minus x squared when x is greater than 1. This x is, see the minus there, means as x approaches 1 from the left. Those values are like 0.9 or 0.99 or 0.999. See how those are getting closer and closer to 1 from the left? In other words, values that are smaller than 1, and that is shown by x is less than 1. That means from the left, we're going to use this function right here, 4 minus x, or this part of the function rather. So let's write that down. Limit as x approaches 1 from the left of 4 minus x. Well, that's not a problem. We can plug that in there because we're just approaching from the left. So I'm going to plug in 1, and we get 4 minus 1, which is 3. How about from the right? Well, the limit of f of x as x approaches 1 from the right, those values look like 1.1 or 1.01 or 1.001. Notice how those are getting closer and closer to 1 from the right. So that's going to be x is greater than 1. And right here, we're going to use 4x minus x squared as our function. So let's plug that in. The limit as x approaches 1 from the right, well, there are no problem values there, so we can plug in 1 here. And we get 3. So wait a second, here's my question for you guys. Does the overall limit exist for this function at x equals, as x approaches positive 1 and positive 1? Well, those are the same. So therefore, yes, the limit does exist for this function as x approaches 1, and it is 3. All right, one last kind of problem I'm going to show you guys. These are limits from calculus that we're going to see. So if I give you a function like this, f of x equals x squared minus 1, I want you to evaluate it as h approaches 0 of this function. So notice we've got two functions that we're subtracting, and the x plus 3 is the input of one of the functions, and the 3 is the input of the same function but later. So first we just need to write this down. What is this equal to? Well, if we plug in x squared minus 1, we plug in 3 plus h into that, this is what it's going to look like. Plug in 3 plus h into x squared minus 1, and then subtract 3 squared minus 1. Those brackets are just another way of writing parentheses to differentiate which parentheses go with which parentheses. So don't freak out about the brackets. They're just fancy parentheses. Let's simplify this because it looks bad right now, and it might look a little worse before it gets simpler. So 3 plus h squared, that's 9 plus 6h plus h squared. You can use a Punnett square for that. We also have the minus 1, and I can simplify 3 squared is 9, minus 1 is 8, so it's all minus 8. Well, look at something interesting that happens. We still can't plug in 0 for h because that would cause the denominator to be 0, but 9 minus 1 minus 8 is 0, so we get this function right here. Now, if you notice, we did have done ones similar to this, where we simplified these, and we know we can pull out or factor out an h, and that allows us to divide out the h. We would not be allowed to do this with a normal function except for we're working inside of the limit. So now we have the limit as h approaches 0 of 6 plus h. This is always the step that students forget. They forget, what do I do now? Well, we can plug in 0 into the function now because it's a nice continuous function. So 6 plus 0 equals 6. And there is our answer. Thank you for watching.